Hi my dear friends, welcome back to another class of Python tutorial. And in this class we are going to conclude our operators. Now next we have bitwise operators. What is a bitwise operator? Now a bitwise operator is used to work upon the binary digits such as zeros and ones. Okay, a bitwise operator is used to work upon the binary 0 and 1, and 0 and 1 are binary digits. What kind of bitwise operators we are talking about? Like you have and this is an AND, which is bitwise operator. Okay, that is logical operator. If you remember, in logical operators, we had covered the AND operator. Similarly, in bitwise version also, we have this AND bitwise operator. Okay, then you have OR bitwise operator. Okay, in logical operators, we used the OR operator. Similarly, in bitwise version also, we have the OR bitwise operator, and this is the sign for OR, and this is the sign for AND in bitwise version. Then you have bitwise NOT operator. Bitwise NOT operator. What is the sign for it? This one. Then you have bitwise XOR operator. What is the sign for it? This one. Okay, this caret sign. Then you have bitwise left shift operator. Bitwise left shift operator. And what is the sign for this? This one. Okay. Then you have bitwise right shift operator, and the sign for that is this one. And already know that bits are like 1 and 0. 1 is for true, 0 is for false. All right. Now let us first have a quick look into these things. Bitwise operator, bitwise and, that is this sign I'm talking about. Okay, bitwise and. What does it say? Between 1 and 1. Between 1 and 1, it will return the last one, since it always looks for 0. As soon as it finds 0, returns 0. In logical AND operator, if you remember, the AND operator always looks for 0. And whenever it finds 0, then and there it returns that 0. Otherwise, it returns the last one. Okay. Same logic goes for your bitwise AND operator also. Bitwise AND means basically this one, and this will also always look for the 0. As soon as it will find 0, it will return 0. Otherwise, it will return 1. Concept is similar as that of your logical AND operator. So for example, here you see print 0 and 0. So as soon as it finds 0, that is this first 0, then and there it will return 0. And that's why here at the first output you get 0 here. Then here print 0 and 1. Again, as soon as it finds 0, the AND operator, it returns 0. Hence here in the second part also you have 0 returned here. Okay. Then here you have print 1 and 0. So here the AND operator always looking for 0. Couldn't get 0 here because there is 1. Then found 0 here and returns this one. This second bit. Okay. And returns this. Then print 1 and 1. Now AND operator always looks for 0, and if it doesn't find 0, it will return the last one. Looks for 0, doesn't get. Looks for 0, doesn't get. And hence it will return the last one only. So this second one is returned here in the output console. Just hit shift plus enter, run this cell. Yeah. Now when I apply the AND operator on decimal numbers like 44, 44 is a decimal number, 74 is also a decimal number. Print 44 and 74. So if you run this, it shall return you 8. Okay. Directly, when you will be working on various projects and when you will be using your bitwise AND operator, and there may be scenarios where you will have to use that AND operator between the decimal numbers, then directly you can get this output 8, and you can that like this kind of output. Say for example 8 you get, and that you can use further. Now concept wise, how does it come? So see, 44 is a decimal number, 74 is also a decimal number, and I'm applying the AND operator between these two decimal numbers. And here in the output, what I'm getting 8, which is also a decimal number. Now, logically or internally, how does it work? First of all, you can use the bin function. Bin function is a function that will convert the decimal number into its binary equivalent. Okay, so that's why here you apply or write bin, and within brackets you write 44. There is this first value 44, and when you run it, you shall get here the binary equivalent. 0b is the notation for binary. Okay, 0b is the notation for binary. And the binary equivalent of 44 is this one, 10110. Similarly, you can find out the binary equivalent of the second number, that is 74. So apply the bin function, and within the brackets you write 74 and just hit the cell, that is run the cell, and you get binary equivalent of 74. 0b is the notation for binary. Okay, and 1001010 is the binary equivalent of 74. Now how does it come here? You see, first of all, uh, for 44, copy this copy these bits for 44. Okay, this one is for 44, don't get confused please. And then for 74 also, copy these bits, the binary equivalent of 74. So here you have the binary equivalent of 44, and here you have the binary equivalent of 74. Okay. Now internally, how does it come? Now basically you see how many bits are there for 44? 1, 2, 3, 4, 5, 6. How many bits you have for 74? 1, 2, 3, 4, 5, 6, 7. So one bit is less in 44. Now in case of applying, whenever we want to apply some sort of operation on binary values, then make sure that the number of bits are always equal. Okay, so here to make the number of bits equal, I will add 10 to the left side of this particular binary value. Okay. Now you see how many bits we have: 1, 2, 3, 4, 5, 6, 7, and already for 74 also, that is its equivalent binary value. Here also we have 7 bits: 1, 2, 3, 4, 5, 6, 7. Okay. Now operation will be possible. What will be the operation like? You see, AND operator always looks for 0, and if it doesn't find 0, it will always print the last one. So here AND operator, it will be applied here bit by bit. So AND operator will be applied here between 0 and this one. Okay, AND operator will be applied between this 0 and this 1. So it will print 0. Between 0 and 1, it will always choose 0. Here again, bitwise AND operation will happen between this 1 and this 0, and definitely the AND operator will choose this 0. Then between this 0 and this 0, it will always choose 0 only, that is the first 0. So the first 0 here comes down. The AND operator, because here we are applying AND operation. Okay. Internally, how it happens, that's what I'm trying to explain here. Then here you have 1, here you have 1. So the second one, that is the last one, will come up here. That's what will be written by the AND operator. Then here you have 1, and here you have 0. So this 0 will be returned. Okay. Then here you have 0, and here you have 1. So definitely here this particular 0 will be returned here. And then finally you have this 0 here and this 0 here, and the first 0 will be returned here by the AND. Okay. Now, so this will be your binary. This is the binary output that we get here. Okay, and please remember, for binary operations, make sure that the number of bits are always equal. Like for 44 and 74, their respective binary values, I made them equal in terms of number of bits, in terms of length. Okay. Now, what you can do here is you can use the int function. Int function will convert it into integer, that means into decimal format. The int function will convert it into integer, that is decimal format. And I want to convert a binary value here. Okay, I want to convert a binary value here. What is the notation for binary? 0b. Now copy this entire binary value, 000100, and paste it here. So inside the int function, you have the binary equivalent value, and hit shift plus enter, and here you get 8. Okay, and that's what we got here. When we directly applied print 44 and 74, then we got the output as 8, which is your decimal value. And internally, if you want to go out logically, that internally how it's operating, then this is how you should analyze. Okay, so ultimately this is what we get, 8, which is the decimal equivalent of this particular binary output. And this binary output we got by applying AND operation between these binary values bit by bit. Okay. Then similarly here also the same thing, print 11 118, sorry, print 118, then and then here you have 30. Okay, so directly if you run this, here you see we get the output as 22. The AND operation, bitwise AND operation between 118 and 13 returns you the value, the decimal value as 22. This decimal value of 22 is my required output. Now again, if you want to go out analytically how it happens internally, then again use this bin function to convert into binary. That is the first operand we shall use, that is 118, and you place it inside the bin function and hit the enter, shift plus enter, run this cell, and here you have the binary equivalent of 118. Similarly here we go to the next cell and apply the bin function on the second operand, which is 30. So you get the binary equivalent of 30 here. Okay, 0b is the notation for binary. Now if you want to measure it analytically bit by bit, just copy this. This is the binary equivalent of 118. Place it here, all these bits, and then copy this binary equivalent of 30. Copy this binary equivalent of 30. Okay. Now you see, this is for 118, isn't it? This one is the binary equivalent of 118, and here you have the binary equivalent of 30. Okay. So how many bits here you have? 1, 2, 3, 4, 5, 6, 7. And here how many bits I have for 30? 1, 2, 3, 4, 5. So you, what you can do is that you can add, that is here you have 7 bits for 118 and here you have 5 bits for 30. Now in order to ensure that bit by bit operation happens, that is binary operation happens between these two binary values, we got to make sure that the number of bits for both are always equal. And that's why in case of binary system, we, what we do, we add zeros to the left hand side. How many zeros we need here? 2 zeros. Then only you will see altogether this entire length shall become 7. There is the number of bits here will become 7, while the value remains same, the decimal value remains the same. Okay, because adding zeros to the left side, it does not change the value, only helps in modifying or altering the total number of bits, that is the length. Now, what will be your and what will be your output after applying the bitwise AND operator between these two binary values, bit by bit? Okay, between these two binary values, bit by bit. Here you see again, between 1 and 0, it will return 0. Here between 1 and 0, it will return 0. Here between 1 and 1, it will return 1, isn't it? That is between this one and this one, it shall return 1, and between this 1 and this 0, it returns 0. Between this 1 and this 0, it returns 0. Okay, then between this 0 and this 1, it returns the AND operator, bitwise AND operator will return 0. Then between this one and this one, the bitwise AND operator will return 1. That is this second one I'm talking about. Here also the second one was returned. Then again, between this one and this one, this second one will be returned. Okay, and between this 0 and this 0, the first 0 shall be returned here. Okay, now we have to check, this is the binary equivalent. Now we are cross checking here whether the decimal equivalent of this entire binary value, whether it is 22 or not, should be 22 logically speaking. So what to do, you have to apply the int function. Okay, you can simply apply the int function, and that means int function shall convert the binary value into its decimal equivalent value. So first of all, inside this you need to take your binary value. So for that you need this 0b, and then copy this entire thing, 10110. Adding zeros to the left hand side doesn't alter the value, so you can skip those zeros. That's why take the relevant values only, relevant bits. So 10110 inside this, and before that you have 0b. So this entire thing is your binary value, and converting it into decimal value. So run this cell, hit shift plus enter. You see, after run this cell, the answer is 22. So yeah, it's all good. Then just a recap of your like number system. 0 comma 1, it is for binary number system. What is the base? Base is 2. And what is the notation? 0b. Then here you have 0 to 9. 0 to 9, there is the range, is for decimal number system. What is the base? Base is 10 and it is for integer values, decimal values. Then 0 to 7 is for octal number system. And what is the base? Base is equals to 8. What is the notation? 0O. Okay. Like for binary, you have the notation 0b. For octal, you have the notation as 0o. That, yeah, this one is an octal value. Then 0 to 15 is for hexadecimal number system. And what is the base for hexadecimal? 16. And for notation, what we use? 0x. Okay. And here I've stated the int function. This int function transforms into decimal value. Then the oct function, oct function transforms into octal value. The hex function, this hex function transforms into hexadecimal value. Okay, very simple examples I've taken here. That is like, see, for example, 26 transform decimal to, this 26 is what? This 26 is nothing but your decimal value. So transform decimal to binary, octal and hexadecimal. So first of all, uh, take this variable a, and a is equals to 26. Inside a you have 26. Now apply the bin function, on a, apply the oct function on a, and apply the hex function on a. So when you apply bin function on a, what it shall do? It shall convert decimal to binary. When you apply the oct function of on a, it shall convert decimal to octal. When you apply the hex function on a, it shall convert decimal to hexadecimal. And here you go, accordingly you have the results. Here you see binary equivalent of 26, then octal equivalent of 26, hexadecimal equivalent of 26. For binary notation, you have 0b. For octal, you have 0o. For hexadecimal, you have 0x. Okay. Then next cell, that is this one you see. Again, this is a binary value. Okay. As you can see, the notation 0b, and after that, you have binary digits. So this altogether is a binary value. And transform binary to decimal, that is integer format, then octal format and hexadecimal format. So again, a is equals to, then take this given binary value, and inside a you have this binary value. Now apply the int function on a, then apply the oct function on a, and apply the hex function on a, and accordingly you're printing all of them. That's why outside you're using this print function. Okay. And when you run this, here you see this is the decimal equivalent of the binary value. This is the octal equivalent of the binary value. And this is the hexadecimal equivalent of the binary value. And this is the given binary value. Okay. Then similarly, here you have this octal value. 0O means that the value is an octal value. 0O32. Transform octal to decimal, that is integer format, binary format, and hexadecimal format. Okay. So inside a variable, you have this value 0O32. So apply the int function on a. Because applying int function on a, what it shall do? It shall convert this octal value into decimal value. Then apply bin function on a, what it shall do? It shall convert the octal value into binary value. Then apply hex on a, what it shall do? It shall convert the octal value into hexadecimal value. Run this cell, and here you go. This is the decimal equivalent of 0.032, where 0.032 is what? That is your octal value. Okay, this one. Then here you have the binary equivalent of 0.032, and here you have the hexadecimal equivalent of 0.032. Then next you go into this cell 0x1a. Okay, 0x means for what? 0x means that you have a hexadecimal value 0x1a. Convert hexadecimal to decimal, that is integer, binary, and octal. So now you have to convert the hexadecimal value, that is 0x1a, into your decimal, that is integer, binary, and octal. So again, inside a variable you have 0x1a. Now print int of a. It shall do what? It shall convert the hexadecimal, that is this particular value, into integer value, that is into decimal value, and the answer you get is 26. Then print bin of a. It shall do what? Here you are applying the bin function on a variable, so it shall convert the hexadecimal value 0x1a into its equivalent binary value. And then here you have the oct function. Oct function you're applying on variable a, so it shall do what? It shall convert the hexadecimal value into the required octal value, and the answer you get here is 0032, which is the octal equivalent of 0x1a, and this is the binary equivalent of 0x1a. Just run this cell, hit shift plus enter. Now similarly you have bitwise OR operator. The next bitwise operator is your bitwise OR operator. And what is the sign for OR? This one. Okay. And logical OR already we have covered in our previous class. And if you have not covered that, you can kindly check those videos. Logical OR operator is always looking for one. The logical OR operator is always looking for one. As soon as it finds one, returns one. Otherwise, it will return zero. The same concept here also goes for the bitwise OR operator. Here you see between 0 or 0, the bitwise OR operator will always return the last 0, since it always looks for 1. As soon as it finds 1, returns 1. So just the opposite of bitwise AND. Here you have bitwise OR, which is always looking for 1. As soon as finds 1, returns 1, otherwise returns the last 0. So here you see print, then 0 or 0. This is the sign for bitwise OR. This one we use for bitwise OR. So 0 or 0. It always the OR operator here, bitwise OR operator, always looking for 1. Cannot find 1. Here also cannot find 1. So returns this second 0. There is the last 0. Here print 1 or 0. As soon as it finds 1, that is this one, it returns the 1 here in the output console. Okay. Then print 0 or 1. Here you have the bitwise OR operator. It is always looking for bitwise OR, always looking for 1. Couldn't find 1 here. Here it found 1 and returns the 1 here. Okay. Then print 1 or 1. Print 1 or 1. So here you have the bitwise OR operator and always looking for 1. As soon as finds 1, there is the first one. It returns 1. Okay. So just run this cell. Then here you go, print 57 or 89. Now here you will have to apply bitwise OR operation between these two operands. First operand is your 57, second operand is your 89. Both 57 and 89 are what? These are decimal values. And when I apply this bitwise OR between these two decimal values, print 57 or 89, where OR is the bitwise OR, then you get your answer, which is in the decimal format 121. Okay. Now if you want to check it, that is cross check it, and want to measure how it internally goes analytically, then again apply the bin function for converting the decimal into binary on the first operand. The first operand is what? That is your 57, and here you go, here you have the binary equivalent of 57. Then take the second operand, which is what? Your 89. So apply the bin function on 89 so that we can get the binary equivalent of 89, which is this one. Okay. Now again, just for documentation purpose, I use the hash. And what to do? Here you take these significant, these relevant binary bits of the binary value for equivalent 57. This is the this for 57. Okay. Then take these binary bits and place it here. This one is for 89. Okay, just for reference. So this is the equivalent binary for this is the equivalent binary value of 57. This is the equivalent binary value of 89. Now here we will apply bitwise OR operation. Internally how it goes. So for that, make sure that the number of bits are always equal for both the values. Here how many bits we have? 1 2 3 4 5 6. Here how many bits we have? 1 2 3 4 5 6 and 7. So what to do here? You just simply add one extra 0 to the left side. Okay, so that bitwise binary operation is possible, because we have to ensure always that the length is always the same for the binary values. For both the binary values, the number of bits should be same. There is the length should be same for binary operation bit by bit. Now here we are going for bitwise OR operator. Between 0 or 1, it will always choose 1. So this one. Between 1 or 0, it will always choose the 1. So 1 is returned here, that is this one is returned. Okay. Then here you have this particular one and this particular one. So as soon as it finds one, it returns one. So this first one will be returned here. Then again here you have this one and here you have this one. So it will always return this first one here. So it is returned here. Then here you have 0 and here also you have 0. So this second 0 will be returned because the bitwise OR is always looking for 1. Otherwise it returns the last 0. Then here you have 0 and here you have 0, and it will return the last 0, which is this one, which is basically nothing but your this one. Okay, so that will be returned here 0, and then between this one and this one it will return the first one, so that is this one. Okay, now we are cross checking here. The decimal equivalent of this binary value should be 121. This is a binary value only. So let us check how to check. Apply the int function. So inside this you will have to place at first the binary notation, that is 0b, and then you can place the overall binary value, which is this one. So copy this and place it here and run this cell, and here you go. Yeah, so our method is correct, 121. This is the equivalent decimal value of our output. Which is output? This output we got how? By applying the bitwise OR operator between these two, 57 and 89. Internally, binary equivalent of 57 will be obtained, binary equivalent of 89 will be obtained. Then the bitwise OR operator will be applied between these two binary values bit by bit, and finally we shall get the binary output yielded by the bitwise OR operator, and from there we can convert it into its equivalent decimal value, and here we go, we have 121 by applying the int function. Okay, next we have this is simple. Next we have bitwise operator. The next bitwise operator is your what? Bitwise NOT operator. Bitwise NOT operator, and the sign for bitwise NOT operator is basically this one, and it has got a simple formula, that is this NOT num, that is for number, is equals to minus, then within brackets the number, that is num, plus 1. So here you have bitwise not operator. This for bitwise not operator. The sign you have to write here, that is this bitwise not. Simply you can find it on your keyboard, then give a number like say for example 30, and she'll return you the value, that is minus 31. How we are getting it? Simple, by the formula minus of num plus 1. What is the num here? It is 30. So 30 plus 1. Okay, and ultimately minus of 30 plus 1 will be what? It will be minus 31. Then next we have is your the next bitwise operator. These are all bitwise operators that we are talking about. The next bitwise operator is bitwise XOR operator. Bitwise XOR operator. And what is the sign for that bitwise XOR? This caret sign. And what is the concept here? Identical digits result in 0 and opposite digits result in 1. Please remember this. So first of all, suppose you have 70 and then you're applying this caret sign. This caret sign is what? Bitwise XOR. Bitwise XOR operator is represented by this caret sign. Then you have the second operand, which is 91. So 70 bitwise XOR 91. Directly you can get the result, and here you have your output result, which is 29. Okay, now how to cross check it? Simple. You find the binary equivalent of 70. 70 is a decimal value, and you apply the bin function on 70, so you will get the binary equivalent of 70, which is this one. This is the equivalent binary value of 70. Similarly, apply bin function on 91. 91 is a decimal value, and here you shall get the binary equivalent of 91. Okay, and now how to cross check it? Simple. Just I'm commenting out here. Take these binary digits or binary bits of 70, then take the binary bits of 91. That is, suppose you have to do it analytically. Okay, then This should be the approach. Otherwise, directly when you're using your system, you can directly simply just run the cell and you will get your output. But sometimes you may have to think them analytically. So that's why I'm explaining these things, how we are going analytically. That is how internally these things give you these kinds of results. Okay. That is, we are doing cross checking here. So how many bits here you have? 1 2 3 4 5 6 7, and this is for your, this is the binary equivalent of which value? 70. And here how many bits you have? 1 2 3 4 5 6 7. So no problem, here length is same. There is number of bits are same for both the decimal values. That is for both the binary values. Okay. Here also you have 7 bits for this binary value. Here also you have the 7 bits for this binary value. And this is the equivalent binary value of 70. This is the equivalent binary value of 91. Okay. Now, what is the logic here? Identical digits result in 0 for bitwise XOR. Identical digits result in 0 and opposite digits result in 1. So let's see. Here you see 1 and 1. Both are here, both are binary values. Both are binary values. And here we are going to cross check by applying bitwise XOR operator between these two binary values bit by bit. So here this one and this one shall be taken into consideration. Bitwise XOR will be applied. Here both the digits are same. So in this case, what should be returned? 0 as per as our logic. Then next, here you have this 0 and here you have this 0. They are identical. So output should be returned as what? 0. Here you have 0 and here you have 1. Bitwise XOR is applied between these two, and 0 and 1 are opposite. So the output that should be returned by bitwise XOR should be what? It should be 1 as per as our logic, isn't it? That is, for opposite digits result in 1. Okay. Then here you have 0 and here you have 1. Opposite digits. So what should be the output returned? 1. Then here you have 1 and here you have 0. Again you have opposite digits. So what should be the output returned by the bitwise XOR operator? It should be 1. Then here you have 1 and here you have 1. Identical. So what should be the output returned? 0. Because what should be the output returned here? 0. Because why? These are identical digits, 1 and 1, isn't it? Next, here you have 0 and here you have 1. Opposite, these are opposite bits or opposite digits. So what should be returned by the bitwise XOR operator? It should be 1. Now let us cross check. Its answer should be 29. This is the binary output that we get thanks to the bitwise XOR operator, which is applied between these two binary values bit by bit. And this is the binary output that we got from the bitwise XOR. And that was not shown here. Directly we got the decimal output. So our requisite is that the decimal equivalent of this binary value should be 29. So let us cross check. Apply the int function on this binary value, and here you can see already I have applied here int, and inside this give the binary notation, that is 0b, and then give these relevant binary digits or binary bits, 11101, and hit the shift, run this cell, and here you see the decimal equivalent of this binary output is 29. So our this answer and this answer are same. So our methodology is correct. Then you have something known as bitwise left shift operator. Bitwise left shift operator. So what is the syntax here? Syntax here is, here num, there is the number, then these two arrows you have to give towards the left side, and there, and after that you will have to specify number of bits. So here some rules are there, or the concept is here for bitwise left shift operator. First, convert the given number into its binary representation. Next, express the binary number in a 32-bit format. Then discard the specified number of bits from the left side and append an equal number of zeros to the right side. And then finally convert the resulting binary value back into its decimal format. Okay, you will understand this by some examples. So your first of all, convert the given number into its binary representation. Okay. Now directly how you can do, now like for example here you have 77 And then here you have these two left side arrows, which basically stands for the bitwise left shift operator. And here you have the decimal number or decimal value. After that you have the bitwise left shift operator, and after that here I have given this 4. This is for the number of bits. If you follow this logic, here first of all you have to give the number, then the bitwise left shift operator, then number of bits. So here this is my number, decimal number, then bitwise left shift operator, that is these two arrow signs towards the left, and then the number of bits. So overall we are performing here bitwise left shift operator. Run this cell, 77 bitwise left shift 4, and here is the answer 1232. Directly this is how you're getting it. But in some exams you may not have your system, and you might have to prove them analytically. So that's why I'm going to explain the procedure here. That is what is happening internally. First of all, here you have one decimal value only, that is the 77. Please don't get confused. This 4 is actually for your number of bits. Number of bits. Okay. So as per as our concept of bitwise left shift operator, internally what happens? First, convert the given number into its binary representation. So you apply the bin function on 77, and you get your binary equivalent value. Binary equivalent value of 77 is here. Okay. Next, what? Next, express the binary number in a 32-bit format. So let us check here. First of all, put the hash, and then copy all these relevant bits, binary bits, place here. That is besides here. Okay. How many bits we have here? 1, 2, 3, 4, 5, 6, 7. 7 bits we have here. 7 bits. And what is the rule? That is, you have to convert it into a 32-bit format. So 7 bits are here, 1, 2, 3, 4, 5, 6, 7. What will I do? I should add 25 number of zeros towards the left side of this entire binary value. Towards the left side of this entire binary value, I will have to add, I will have to add 25 number of zeros. So what will happen? There are 25 bits of zeros, and here how many bits you have? How many number of bits you have? 7. So 25 plus 7 will be 32, and that's how you will be able to convert your binary number into a 32-bit format. Adding zeros to the left side doesn't change the value, simply changes the length or the number of bits. So here you have 7 number of bits. So towards the left side, if I add 25 number of zeros, that means 25 bits are there. Then 25 plus 7 will be 32. So this entire binary value shall be converted into a equivalent 32-bit format, where the overall value will remain the same, length changes. So 5 zeros first I add here, 1, 2, 3, 4, 5. So 5 zeros you have, I need 25 zeros. So copy this 5 zeros and paste here. Now you have 10 zeros, paste again. Now you have 15 zeros, paste again. Now you have 20 zeros, paste again. Now you have 25 zeros. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25. So 25 bits here you have, 25 number of bits of zeros you have here, and here together you have 7 bits. So 25 plus 7 is 32. So 32-bit format has been done. Next is your discard the specified number of bits, whether it be 0 or 1. Whether be it 0 or 1, you will have to discard the specified number of bits from the left side and append an equal number of zeros to the right side. Now, what is it saying here? Discard the specified number of bits from the left side. What is the specified number here? This one, this 4. Specified number of bits. Specified number of bits here is nothing but your 4. So you will have to remove 4 bits. You will have to remove 4 bits from the left hand side. So these 4 bits, whether be it 0, whether be it 1, you will have to basically discard 4 number of bits from the left side. Okay. So these 4 number of bits should be discarded, and the rest you can copy. So copy the rest number of bits and place it here. Okay, and then append equal number of zeros to the right hand side. That means onto the right hand side you will have to append equal number of zeros. That means 4 number of zeros, because here the specified number of bits is how much? 4. And by the rule you will have to discard 4 number of bits, whether those bits be 1 or 0. You'll have to discard those 4 number of bits from the left hand side, then take the rest number of bits and then simply place them here. And after that, onto the right hand side you will have to add equivalent or append equivalent number of zeros with respect to the number of bits. Number of bits is how much again? 4. And 4 number of bits were removed here from the left hand side, and equivalently 4 number of zeros bits you will have to add here. That is equivalent 4 number of zeros you will have to append here. This is the rule. Now simply apply the int function. Simply apply the int function inside this. Take 0b for binary notation. Now all these zeros no need to take, because zeros added to the left hand side doesn't change the value. Take the binary value where it starts from 1. So 100, 1101, and these 4 zeros. Well, when zeros are added to the right hand side, then values they do change, so you cannot discard those. Now place here and run this cell, and you check, cross check here. Here we get 1232, and here also we got 1232. So our cross check is correct. That is the methodology is correct. Then another, here apply the bitwise left shift operator on 48. The required decimal number value is 48, and here you have to apply bitwise left shift operator. So give these two arrow signs towards the left hand side, and then here you'll have to basically write the specified number of bits, which is here 5. 5 stands for the specified number of bits. Directly here I will get my output, which is your 1536. It is decimal equivalent only. Here also it was decimal equivalent only. Okay. Now directly in one line, this is how we can get the answer for bitwise left shift operator, which is your 1536. And it was when we applied the bitwise left shift operator on this decimal value 48. And specified number of bits is how much? 5. Now for theoretical cross check, what you can do is you can apply the bin function on this decimal value 48, and here you will get your equivalent binary output, which is 0b, double one, and all these zeros. Okay. So first of all, what were the steps internally that happens? Convert the decimal number into its equivalent binary value. That's why I applied the bin function on this decimal value 48, and we converted this into the binary value. Now copy all these bits, place here. Okay. How many bits here we have? 1, 2, 3, 4, 5, and 6. 6 number of bits here we have, and you have to convert this binary value into an equivalent 32-bit number system. You will have to convert this into a 32-bit format. Do we have 32 number of bits here? We don't. How many bits we have? 1, 2, 3, 4, 5, 6. That means this time here you will have to add 26 number of zeros towards the left hand side. 26 number of zeros here you will have to add towards the left hand side. So 26 zeros bits you'll have to add to the left hand side. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10 zeros are added. Just copy this and place here. So now 10 plus 10 is 20 number of zeros here you have. That is 20 number of bits of zeros. And now 6 more are required, because 26 additional number of bits are required. 20 already here we have. 6 more. So add 6 more zeros. 1, 2, 3, 4, 5, 6. Okay. So already here how many number of bits we have? 26. And here how many number of bits we have? 6. 26 appended with 6 shall give you 32 number of bits. So now this binary value has been converted into its equivalent, the 32-bit format. Okay. Now what was the next rule? That is, discard the specified number of bits. Discard the specified number of bits from the left hand side. Specified number of bits is 5, and you'll have to discard 5 number of bits from the left hand side. 1, 2, 3, 4, 5. Whether these bits be zeros or ones doesn't matter. You'll have to discard the specified number of bits from the left hand side. Specified number of bits is how much? It is 5. So discard 5 number of bits from the left hand side. 1, 2, 3, 4, 5. So these 5 bits you'll have to discard. So what to do? You can copy the rest number of bits. You copy the rest bits, that is this one, and paste here. Then what was the next step? That is append or add equal number of zeros to the right hand side. That means 5 number of zeros onto the right hand side, because here the specified number of bits is how much? 5. Okay. And here we discarded or removed 5 number of bits from the left hand side. So equivalently, you will have to append or add 5 number of zeros to the right hand side. 1, 2, 3, 4, 5. Okay. Now convert this into your binary format. So use the int function. Use the int function and take this entire number, binary value, place it here, and here you have to give 0b notation. Run this cell. Now here you get 1536. Here you get 1536. Okay. So our methodology is correct. Here also 1536 and here also 1536. Okay. There is another way also, where you can do your bitwise left shift operator. For example, 48 into 2 to the power 5. 48 is the equivalent decimal value, and 5 is the number of bits. Like here, 48 is the equivalent decimal value, and here the 5 is for the specified number of bits. So 48 into, that is the number, into, that is this, into 2 to the power, this is for 2 to the power, these two asterisks. This single asterisk is for multiplication and these two asterisks is for to the power. Then the specified number of bits, which is 5. So 48 into 2 to the power 5 shall give you 1536. This is also an alternate way via which you can do your bitwise left shift operation. Okay. Then for example, here if you remember this particular example, 77 bitwise left shift 4. So the alternate way of doing bitwise left shift operator is take the number which is 77 into 2. Okay, this 2 will be common for all the bitwise left shift operator when you are doing them analytically or doing in alternate way. So the number which is decimal number, that is 77 into 2 to the power, these two asterisks is for to the power the number of bits, which is nothing but your 4. So 77 into 2 to the power 4, and that shall give you 1232. So the actual formula is basically the number into 2 to the power the specified number of bits. This is the formula. Okay. And here if you run this cell, 1232. Okay. Similarly, there is, you have bitwise right shift operator. In the bitwise right shift operator, what you will have to do is first convert the given number into its binary representation. Next, express the binary number in a 32-bit format. Then discard the specified number of bits from the right side. In bitwise left shift operator, what I was doing, discard the specified number of bits from the left side. Here you'll have to discard the specified number of bits from the right side and append an equal number of zeros to the left side. Okay, and append an equal number of zeros to the left side. Finally, convert the resulting binary value back into its decimal format. Okay, so how that is happening? Here you see, here you have the value 72, and here we are applying bitwise right shift operator, that is the two arrows towards the right hand side, and then here we are writing the specified number of bits, which is 4. 72 bitwise right shift 4. Just run this cell directly, you will get your output, that is 4. Now, if you want to cross check it analytically, then this is the decimal value, and this only we have to take to convert into binary value. Take the bin function, and inside the bin function you place this decimal number 72, and you will be able to convert the decimal number into its equivalent binary value, bin 72, and here you get your binary value 0b100100. Okay. Now take this 100100. How many number of bits here we have? 1, 2, 3, 4, 5, 6, 7. 7 number of bits here we have. And we know that this is ultimately a binary value only. This you have to convert into what? Into 32-bit format. Okay. So here already you have 7 number of bits. 1, 2, 3, 4, 5, 6, 7. So you will have to add 25 additional number of bits towards the left hand side. That is 25 additional zeros, because ultimately the value I want to remain the same. So by adding zeros to the left hand side, the value overall remains the same. So you can add here 25 number of zeros to the toward to on the left hand side. 25 number of zeros. There is 25 bits of zeros on the left hand side. So 1, 2, 3, 4, 5, and take these 5 zeros, copy and paste. So 10 zeros, paste again 15 zeros, paste again 20 zeros, paste again 25 zeros. So how many number of bits here you have? 25 number of bits here you have. 25 number of bits of zeros here you have. And appending with how many number of bits? 1, 2, 3, 4, 5, 6, 7. So 25 plus 7 gives 32 number of bits altogether here you have. So we have converted this binary into we have expressed the binary number into a 32-bit format. And now what is the rule here? The rule here is for bitwise right shift operator, discard the specified number of bits from the right side. Discard the specified number of bits from the right side. Okay. Specified number of bits, how much? 4. So you will have to discard 4 number of bits from the right side. So that means these 4 bits you will have to discard from the right hand side. And then what? And add and append an equal number of zeros to the left. That means towards the left hand side you will have to append 4 number of zeros. Okay. So as per as our rule, as per as our rule, here you will have to discard the specified number of bits from the right hand side. Specified number of bits is what? It is 4. So you will have to discard 4 number of bits from the right hand side. So take the rest, copy and paste here. And what you have to do, append an equal number of zeros to the left. So that means 4 number of zeros to the left side. 2, 3, 4. Okay. This is just the opposite of bitwise left shift. Okay, just remember, rest the concept remains the same. Only the left and right are the opposites in case of bitwise left shift and right shift. So now let us cross check by applying the int function on it. So int, then take this. See, from here to here everything is 0. Taking them won't make any sense. Start taking from where you'll have start taking the binary value where it starts with 1. So 1 double 0. Then here 0b and paste this. So int 0b 1 double 0 and run this cell 4 we get. Okay, this is the decimal equivalent output of our binary output that we got. And see, in both the cases we are getting 4. So yes, our methodology starting from this cell up to this cell is perfectly accurate. And all these 3 steps are being performed at once here only. Okay. And just like bitwise left shift, we had an alternate way. In case of bitwise right shift, also we have got an alternate way. For example, here 72, 72. Then this is for float division. If you remember these signs, there's this is a division sign. This is also a division sign. And when you combine these two division signs side by side, then it becomes float division. So 72 float division, 2 will be common here. Then here you have 2 asterisks. That means to the power. And then here you have to specify the number of bits. So here you have to take the number, decimal number, that is 72. Then you have to give this float division, that is these 2 division signs. Then 2, these 2 you have to write. Then for to the power, you have to write here 2 asterisks and then mention the specified number of bits, which is 4. So 72 float division 2 to the power 4. Run this cell and here you get 4. This is an alternate way. This is also an alternate way for your bitwise right shift operation. Okay. Similarly, you can have 88 as your decimal value, and then here we are writing this bitwise right shift, that is the two arrow signs towards the right hand side. Then here you have the specified number of bits, which is 3. And our every we will, if you run this cell, then here we get our required output, which is 11. How we are getting this 11? Again, the same procedure you have to apply the bin function on the number 88, and you will get your equivalent binary value. Then convert the binary value into a 32-bit format, and then you have to basically discard the specified number of bits from the right hand side. That is, you'll have to discard 3 number of bits from the right hand side, and then append equal number of zeros to the left hand side. That is, you have to add the 3 number of zeros to the towards the left hand side, and then you get your output binary. You get your binary output value. Take that and apply the int function on it, so that you can get your equivalent decimal output, and that should come out to be as 11. Okay, so this is the bitwise right shift operator. 88 then give these two arrows for bitwise right shift, and then here the number of bits. Here you have the decimal operand, and run this cell, it is 11. So if you want to do it in an alternate way, then for bitwise right shift, what to do? Write this number, which is decimal number 88, then give this float division sign. There is these two division signs you have to use. Then write 2, then you have to write to the power, there is these two asterisks, and then you have to mention or write the specified number of bits. What is the specified number of bits here? It is basically 3. Okay, so 88 float division 2 to the power 3, and that shall give you 11. Okay, and here are the steps I've done again. Take the, if you want to do it analytically, then you have to convert this decimal 88 into its equivalent binary. So apply the bin function on 88, and here you get your binary. Now take this, take the binary value of 88, that is 10110000. Place it here. How many bits here we have? 1, 2, 3, 4, 5, 6, 7. 7 number of bits here you have. You have to convert this binary value into a 32-bit format. So that means towards its left hand side, how many number of zeros you must add? 25 number of zeros you must add. That is, 25 number of bits of zeros you must append towards the left hand side, so that the overall value remains the same, length changes, so that overall you are able to convert this binary value into a 32-bit format. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Copy these 10 zeros, paste. So now how many zeros here you have? 20. We need additional 5. So 1, 2, 3, 4, 5. So now here we have, up to from here to here we have 25 number of bits of zeros, and then additionally we have 7 number of bits. So together it becomes 32 number of bits, 25 and 7, when we are appending it. Now what is the rule? This is we are doing for bitwise right shift operation. So here you will have to discard the specified number of bits from the right hand side. Specified number of bits is how much? 3. So here you will have to discard specified number of bits, that is, you have to discard 3 number of bits from the right hand side. So these 3 zeros you'll have to discard from the right hand side, and then take the rest of them. Take the rest. So take the rest means from here to here. Okay, place here, and then further what you have to what you have to do, append equal number of zeros towards the left hand side. That means if there are 3 number of bits that have been removed, there are 3 number of bits that have been removed from the right hand side, then on the left hand side you will have to append equal number of zeros. So here we discarded 3 number of bits from the right hand side, so that means on the left hand side we will have to append 3 number of zeros. 1, 2, 3. Okay, 3 zeros we have appended on the left hand side. That's what it says. That is, whatever will be the specified number of bits that will be removed from the right hand side, equivalent number of zeros have to be appended on the left hand side. Okay, and this is our binary output. Now all these zeros no need to take. You can directly take 1011, where the binary value starts from 1, because zeros on the left hand side do not change the value, and then apply the int function on it. So take the int function 0b, place this, and here you go, 11. So our bitwise right shift operator here, when we are going step by step analytically, it is yielding 11, which is same as that of this particular cell where we ran 88 float division 2 to the power 3, and same as here, that is when we directly ran it, that is 88 bitwise right shift 3. Here also we got 11, here also we got 11, here also we got 11. So our procedure is correct. Okay, so that's it for this class. If you have understood this class, then you can hit the like, share, and subscribe button and press the bell icon for notifications. And thank you.